Good afternoon all. It's my great pleasure to introduce today's speaker, Professor Omlan Chakraborty. He is the full professor and the director of the A.K. Choudhury School of Information Technology, University of Calcutta. He is the former dean of Faculty of Engineering and Technology of his university. He completed his MTech from University of Calcutta and did doctoral research at Indian Statistical Institute. He was a postdoctorate fellow at the School of Engineering, Princeton University, USA. He has almost 20 years of experience in engineering education and research. He received the prestigious DST Boy Scout Fellowship Award in Engineering Science, Indian National Science Academy, Visiting Faculty Fellowship, JSPS Invitation Research Award, Erasmus Mundus Leaders Award, Hemit Visiting Professorship from University of Cambridge, UK, and Shikhar Ratna Award by Department of Higher Education, Government of West Bengal. He has received multiple project grants in the area of embedded system, VLSI design, quantum computing, computer vision, cyber security, IoT, and medical image analysis from different funding agencies like DST, MAIT, DRDO, DAE, MHRD, Ministry of Social Empowerment, UGC, TCS, Intel, India, etc. He has also served in various
Yeah, there is some network issue most probably.
I think, yeah, she got disconnected. So no issues. I can start. She has already given a lot about.
So actually,
I think, yeah, rain has started. Yes.
Yes, sir. So, sir, actually there is some formality we have to do this, sir. So, on behalf of the CSE department, sir, I would like to welcome in our college, and I will also like to welcome our webinar there. So, it is great feeling for me that under whom I have done my BTech project there, and now I am welcoming that person for the webinar there. So, it is a great feeling and the one type of privilege I am feeling right now, sir. So, sir, because we know that the participant already joined through the YouTube live, so I would like to request you, sir, kindly start the session and enlighten us through your knowledge that. And I hope that after this webinar, student can get the idea and they can implement in their research, sir. So I would like to request you, sir, kindly start the session. Thank you, sir. Over to you, sir.
Yeah, thank you, Dhanpal. Yeah, that means it's great to be invited by the students. You are my BTech student, and Jilam is my MTech student, and also the PhD student. So so the students are doing good. That's also a very good for the faculty. And thank you all, and thanks to the GIS Engineering College for inviting me. I know the institute very well. I am very connected to many of the persons in the institute, but it's always good to get invited from a good institute. So, my today's lecture, what I will be delivering is basically a very it's a So the lecture will be on deep networks, which is we know that this is the very interesting as well as very popular machine learning approaches, which comes under the approach of deep learning. So I will try to give a brief overview of what is deep convolution networks, right? And then also I will give you some important aspects okay, of using this okay, these deep neural networks, okay, using a very important application which is a spatiotemporal fusion, okay, because we know that though image processing is a very important aspect of many of our computational tasks, but video processing is also an equally interesting and equally important. So how we can escalate the concepts of deep neural network from the image processing, and then we can take it on towards the video processing, especially using the spatiotemporal fusion. That will be my key topic in this particular lecture. So I will try to go slow. I have around 40 plus slides, which I will try to finish by maybe by 100 or 110 minutes. And what I will also do, I will give pauses in between my lecture. Suppose when I finish an important concept, then I will go back to the participants. I will take a couple of questions which you can put into the chat, okay, and I will answer those questions. And again, I will come back to the question and answer after I end this talk. I understand that this talk is basically for the MTech, for the early faculties and some of the faculties of this institute, as well as the students. So I will try to make it a mix, which is composed having some fundamental concepts, and then I will try to slowly push that towards the advanced concepts. So let me start. I hope my screen is visible to all of you, right? And I'm audible.
Yes, sir. Yes, sir.
Okay. So we know that we are in the era of deep learning. So machine learning, deep learning is a particular way of doing machine learning. We are trying to abstract knowledge. But what is specialty in deep learning compared to the other domains of machine learning is that deep learning tries to abstract the deep knowledge which is present in the data. What is meant by deep knowledge? The deep knowledge means that we try to capture very minute information we try to abstract very minute features of the data, right? And try to use those features for classifying, for recognizing the objects, for classifying the images, and so on. So it also follows the hierarchical representation. Hierarchical representation means we know that we add letters to form words, and words to form sentences, and sentences to form context, right? Sentences to build a story. So that is very important. In the domain of feature also the same thing happens, right? It depends that how far we can abstract from the given data. So the lower level features can be considered as we have identified the letters in my language in a given script. Does it make any sense to me? No. As such, if I just tell that, hey, I give you a script which has A, F, D, G, H, M, N, P, L, does it make any sense to you? No, it doesn't make any sense to you, right? Right? It makes a sense if I tell that, okay, if I tell that letter tells that the text tells that I am going to, okay, so I'm going for shopping. That makes a sense to you. So which means that if from the letters, if we can assemble the words, and from the words, if we can assemble the sentence, and we can go further, right? I can tell that I am going for shopping, right? And I will be purchasing for my family. Okay, there is a Durga Puja, or there is a Diwali, or there is a Eid al-Fitr for which I am purchasing. Okay, then that gives you a very good context that what type of person I am. I am very much towards my family. I try to spend money for my family. So that also gives a very good context of the nature of the person I am. So So you see that, so you see the more and more higher level you go up in understanding a particular, a piece of data, right? Better, better understanding or more information you can capture. And that's exactly the process what our brain also does. So what deep learning does is a hierarchical way of feature abstraction as it is shown in this particular figure, in this particular flow. What it tells that it's just an image, right? And it tries to understand at first the edges. From the edges it goes to the objects. From the objects it goes to the some sort of connectivity or some sort of co-locality of the objects, and then it tells that, hey, whether this particular image tells you about it's an indoor, it's captured indoor or it's captured outdoor. So you see that it goes with several level of abstractions, and then it tries to classify or it tries to recognize the image, right? And that's and this particular procedure of processing is also very similar to how we do the processing in our nervous system, especially the brain. Right, in brain we know that we have different functional regions, right? And each of the functional regions try to abstract some features from the data what we capture through our senses. That may be our visual senses like eye. That can be auditory sensors like ears. So that was, and sometimes both the visual and the auditory sensors are combined, which is called a fusion, right? And then the analysis about the environment is done, or some inference is generated about the environment. So like different functional regions tries to trap the different features of the input. Similarly, the deep networks also does the same work. It is a several layers of filters, which actually work one layer after other and after other and so on. And in the process, it tries to capture the higher level features. From the primary level features, it tries to go on and try to capture higher and higher level features. And this capturing of higher level features will make this particular classifier, which will be ultimately fed into the classifier, because features are fed into the classifier to classify. And these higher level features, when fed to the classifier can identify or can classify very minute differences among the objects. So that's why deep learning is so important. We'll look into how it is being done in the preliminary part of my lecture. So this image also gives you an idea that how high level features are being generated, from the low level features. So maybe the first image, if you look, this may be the gradient information only. So gradient information in an image means you try to find that, you try to move an operator and try to find that a particular pixel is greater than its neighboring pixel by how much, right? Or by how value, what's the value? And if the value is pretty higher, then you that means or the value is over a threshold, and then you mark the pixel with a white, or with a black, and rest are so you take two colors, which is called the binary image. So what do? If you find that a pixel has a gradient over a threshold, you can mark the pixel as a white, and the pixels which are lower than a threshold, you can mark that with a black. So, but before doing that, you have to find the gradient, and after you do the gradient, you can mark the edges. But after you do the edges, you can find some sort of, whether there is a texture information within the edge information, because edges are also a part of a texture, right, or a part of objects. right? We try to find textures and objects in the particular given image, right? And slowly and steadily, the information, because the abstract from the image becomes better and better, or clearer and clearer, right? And then you can surely classify this particular image. To understand this particular way the filters work in the deep network or a deep convolution network, which is very different, okay, which is a different process from the conventional neural network, right? In the case of conventional neural network, we know that you actually push the entire input as a single string of inputs, right? You give x1 to xn, okay, where all of these are inputs to your neural network. And the neural network, what it does, it tries to do it tries to take a weight, right, and multiplies weights to each of these inputs, different weights to different inputs, right, and try to take a cumulative of this, right? And that's the way a normal neural network works. But what we see in the case of a convolution neural network or a deep network is that it doesn't take the input at a shot. If you see this figure, what it does, okay, if you see this figure, it actually works on the image data, and image data is a two-dimensional data. So the two-dimensional data, what we do, we try to divide the image into certain patches, into certain spatial patches. Why spatial patches? Because if you see the way the patches are defined, these patches cover some pixels which are spatially neighbors. So you try to define a patch, and this patch works with a kernel, and this kernel gives you the same operation what you do in a normal neural network, the weight multiplied by the inputs. So what happens here is that instead of the entire input as a one shot, you take the input in a spatial patches, right? And these are the spatial patches which has been marked, right? And then with each of these spatial patches, you actually work a particular kernel, right? And you do a kernel operation, okay, which actually works with each of the patches, and that is being shown here. So this is the, if you plainly look into this is the kernel operation, right? And this kernel operation is generating an outcome, right? And this outcome is the outcome of the convolution filter or the convolution kernel operating over a patch image. And this work goes on over the entire image by a movement of the kernel over the image, right? And it is again, okay, it forms one particular layer. And when I tell one particular layer, it's not only a single kernel generates the information. In a particular layer, there can be m number of kernels which are doing different, generating different, having different weights, right? And each of the kernels are abstracting different features from the image in the same layer, right? So what you see here is that you see in this diagram, you see that this particular these are each of these are the kernel outcomes. So there is a filter which is working on this image, on the patches of this image, right, and generating a filter outcome which is this, right? And similarly, there are other kernels which are also generating the similar outcome. So in a particular layer, I can have a number of convolution outcomes, which are called feature maps, and each of the feature map will be generated by one particular kernel, and that forms one particular layer of the convolution, right? And then what we can do, we can actually apply an activation function. What is the role of the activation function? The activation function actually tries to pick up those particular outcomes which can really really have a contribution. The outcomes which have the contribution. Okay, so contributions means which can contribute to the outcome considerably. Okay, which means that if the convolution outcome for some of the patches are very small, then they will not be activated and they will not contribute to the activation function. Whereas the outcome which are pretty strong or pretty high, they can be considered by the activation layer and they can go to the as an outcome of the activation layer. So normally in the case of convolution neural network, the activation function is sort of a ReLU, which is a, if I can draw, let me draw it. So the activation function ReLU is something like this. Okay, if this is your 0 and this is your negative axis, this is your positive axis, the activation function looks like this. Okay, what it means that if the outcome is negative, if the outcome is negative, then it will if the outcome is negative, then you will have 0 as your output of your ReLU. But if the outcome is positive, right, it will try to maintain the same value. So what happens in the activation is that all the outcomes, all the filter outcomes which are negative or less than 0 are being discarded, and all the outcomes which are higher than the 0 are being taken for the next layer. Because as I told that we will have a series of these layers. So what it means that I am operating a filter, right? And the filter is generating different values for different patchy regions. Patchy regions means, again, I tell patchy regions means to divide the spatial region into some patches. So you operate a kernel over all the patches. Some of the patches responds good, some of the patches responds low. So next level feature will be contributed by those patches which have responded good. Okay, those who didn't responded good, they will not be considered in the next level of abstraction of the features. So what it is also doing in the process, it is trying to it's doing a sort of downsampling the information, and it's trying to squeeze the information space, and it is trying to take only those features which are important. And slowly and steadily, these high-level features will be sufficient so that the classifier can easily decide that what is this image class. So let's go on this. So as I told that this particular filter, if it works on an image, it's like a filter which actually the center pixel, look into the value, the center pixel. Okay, so the center pixel, so the center pixel operates with the neighbor. So if the neighboring pixels are very close to that of the center pixel, you will see that the value will be 0. Why? I think all of you can tell that there are 4 ones, right? This is especially for the students. Try to understand the operation of the kernel. So if I tell the -4 is the center pixel, and all the 1 which is called the 4 neighbor of the center pixel. So if the pixel is very close to that of the neighbors, then the resulting value will be 0. Okay, but if the pixel is considerably high, okay, than the neighbor, 4 neighbors, then the modulus of that difference will be quite high. So this particular filter, when it walks over the regions of the image, patches of the image, suppose these are the patches of the image. When it walks on the patches of the image, okay, actually the patches will be much smaller. I'm showing much larger patches. So if it works on the patches of the image, right, this filter, right, wherever the pixels are higher than the neighboring pixels, those pixels will get will be marked, right? Or we can tell that wherever the pixels are higher, okay, over the threshold, okay, over the neighboring pixels, okay, okay, and the difference is greater than the threshold, then I can mark the pixel as a white and rest all are black. So if we do that, what we come up is that we come up with with those pixels which determines the edges of my image, right? And that may be the sole contribution. So the sole contribution of this particular filter is that this filter has extracted the edges from the image. Okay, so this is how the fundamental the convolution filters work, right? And this was basically inspired, okay, by an experiment, physiological experiment, okay, done by Hubel and Wiesel, where they showed that our sensors also differentiates and understands. So the basic principle of understanding and information is differentiating from others. So that's the way the edge detection works. So the edge pixels are differentiated from the other pixels by this kernel, and that's the way you understand what are edges and what are not. So now, why these kernels are spatial? This is also a very important question. Okay, the kernels are spatial because spatially local because the image features are also spatially local. Why? Let me try to understand that in a given image, whether I have a bird or not. If I have to find a bird in an image, what I need to find? I need to find head, if there is any beak exists, if there is a head and an eye of the bird, if there are wings of the bird, if any one of them or if majority of them are present, then I tell that is a bird. So what I need to do? And these are all spatially local. It's not that the bird's beak will be everywhere in the image. The bird's beak will be at a particular region of the image. The bird's eye will be at a particular region in the image. And similarly, the wings, the legs, and all things. So this is clearly understood that if we try to trap a bird, we have to understand some local features which are very locally available in the different regions of the image. And that's why the convolution filters works on the spatial patches just to extract the patterns which are spatially co-located. Okay, so let's try to see that. So if we try to work our kernel on this part of the image, which is being magnified here, right? And if I can design a kernel like that, right? The kernel output will be pretty high, and it will tell that it's a big in this region of the image, right? And so my annotation will be, hey, I have found a big. And maybe there is another kernel which has found an eye. There's another kernel which has found a leg. There's another kernel which has found the wings. So I can tell now, hey, that means I have got a particular object which has features like a big eye, legs, and wings, right? And if I tell anyone that I have got an object which is this, that means anyone will tell that, hey, this is a bird. And this exactly makes the job of the classifier simpler, that how the classifier can understand so easily, okay, such a complex information like a bird, okay, in using this, okay, and that's what is, and so now the question is how the filters are being designed. I will come to this very soon, because now the question comes up that I know that how the filter works, but how difficult is to design the filters. I will only give a hint that the convolution neural networks are supervised learning paradigm. So what it means that prior to using the CNN for your specific job, you train the CNN with a set of images for which you know the level. And in that training process, the weights of the kernel gets adjusted so that they can abstract the proper features and can classify the training data, okay, as per the level information. So this training process helps the network to learn about the weights of the kernel. I will not go into that details of how the weights of the kernel are learned, but this is the process how the kernels work and how the kernels work appropriately. So it's a supervised learning paradigm where you push the images having the levels and you try to feed it to the network. Okay, at the initial, the network can go very wrong, but the network will automatically adjust itself by minimizing the error, and more it's minimizing the error. It will generate the weights of the kernels, which will be abstracting the important features of the image, right? And the classifier will become accurate, more and more accurate. So this is what is a big detector kernel. Okay, this may be a okay. So how I come to the big detector? It's another way, but let's try to understand that why the kernel works in the spatial domain, in the spatial patches. Okay. Now, when I'm doing the big detector itself, this is a very important thing in the case of deep learning. It has been told that a deep learning requires a very rigorous training process. Why require a very rigorous training process, right? You have to know that the complex information can have a lot of variations. So detection of peak in a bard A and in a bard B can be a bit different, right? So you have to adjust your filters, okay, in all possible forms, or you have to trap more features, okay, to classify the particular object, right? And so you need a large number of images which will be used to train this. Okay, so you see that to training this large number of images, what you generate the filters which have different forms. So one filter can be a peak which is detected at the upper left, and another can be for the peak which is detected at the middle detector. So by this, the kernel learns that how it will move across the patches. Okay, because the big detector has been detected in the different regions of the image. This is one region, and this is the other region. So all these are adjusted in the training process to make that the network is perfectly trained for any unknown images of birds. For example, this is the detection of bird. So you give plenty images of birds to your network for training, and it will understand all the different types of beaks, all the different types of bird features. Okay, all the spatial distribution of the bird images, and once it training is done, okay, with a large number of images, then the knowledge, the abstraction of the knowledge is being done in a very good way, and then it will be fine to classify any image. Okay, it's supplied image, whether it's a part or it's not a part. So this is what is a convolution filter does. What I have already told you that it works. So this is your image. Okay, the extreme left matrix is an image matrix. Out of the okay matrix, it actually spatially defines a patch, right? And on the patch, this filter works, and this filter records a value corresponding to the estimation of the filter on this particular patch, and the value can be pretty low or pretty high. I have already told that if the value is pretty low, then it will not be not getting excited by the activation function. But if the value is high or positive, it will be taken care. Okay, it will be taken for the next level of decision by the activation layer. Okay, and this filter work on number of image patches which can be seen in the entire image, and it will go on generating the values. To have a better look on this, let us try to see it a very simple way. Suppose I have an image which is a 6x6 image. Okay, try to make it very simple. I have given the value, okay, as only 1 and 0, which means that the image is a binary image. But in the real case, okay, it can have the original color values or the grayscale values, right? Now, this image is acted upon by 2 different filters. Okay, and as I told you that in a particular layer, if you remember my slide number 2, in a particular layer you can have a number of filters. So all the filter 1 and filter 2 and dot, which means there are more filters like this can operate on the same layer, because as I told, each filter tries to abstract a particular feature, okay, a particular feature of the image. Each of the filters, a resultant of a particular layer corresponding to a number of filters, is that in that particular layer, what are the different features you have abstracted, right? So if you try to understand this, let's know that the parameters what needs to be learned, okay, are actually the parameters which are being shown in blue. So the training process will try to adjust the filter. We'll try to adjust the filter so that the parameters are something like this, or the filter parameters are something like this. Why? Why? Can anyone tell me? Can anyone tell me that this is for the students? Okay, I can take a brief pause to the students that why the filter parameters. Okay, if we look into the parameter, that this filter parameter has a typical one in the diagonal, and this filter parameter is the typical one in the middle. Why? Because this filter, if I take filter 1 will give a maximization result in this region of the image, right? Filter 1 will give a maximized result in this region of the image, whereas filter 2 will give a maximization result in this region of the image. So you see that different regions of the image, different spatial patches of the image responds to different feature filters, because the features are spatially located. And that's the important aspect of the image, which has been taken care by the convolution filters. As I told, that this particular filter 1 will give a high value for this particular spatial region, and then it will give a low value. Okay, and this on it will go on. Okay, So you see that it's giving low value for many of the regions, but again it is giving a high value here. It is given a high value here and here. Okay? Because these regions, as I told, this region and this region are perfectly matched with the filter feature. Similarly, this is the filter feature, and that's why it's given high value. Okay, as I have shown. So this is the filter feature, which is mapped exactly the image patch feature, and that's why it's given a high value for these two regions. Now, similarly for the filter 2, if you see the filter 2, okay, you will see the filter 2 has given a high value here, which is for this particular region of the filter, of the image, right? And so what the two filters, if you try to understand the convolution operation with a very simple way, okay, I have applied two filters and I've taken an image. The filters operated on the image patches with a stride 1. Stride 1 means it's a, okay, if you tell stride 1, it means that it's shifting by 1, right? See, this is a stride. It shifts by 1, 1, 1, 1 generates a filter value. So this is the role of the stride, okay? So what I have done, I have worked upon, okay, two filters on the image patches, filters, okay, worked on the patches, and using the stride, it worked on the entire image. And the two filters are generating data in two planes. The back plane is the data for the filter 1, and the front plane is the data for the filter 2. Similarly, it will generate the number of planes, okay, depending on number of filters you have, right? And what are regarding the values? The values corresponding to high values and low values. So low values like this, these are low values, okay? Low values. And these are high values. Okay, so low value corresponds to those particular regions in the image where the filter outcome was pretty low, or the feature abstracted by the filter has a very low value. And the regions and the regions where the filter has got a very high match or has abstracted the feature well, okay, that region generates a very high value. So you see that this itself, if I just show this convolution outcome, you can itself tell that what are the features available in the image and where are those features localized. And these localization of the features, or spatial of the features, are actually used to identify the objects such as a bird. Or maybe it may be, okay, yeah, any object. Okay. So if anyone has any question, especially the students, I can give a pause because I think I've spoken over 30 minutes. So if there is any question, I can take that. Maybe a couple of questions. So if there is any question, I can take the question, okay, or otherwise I will shift to my next discussion. Do I have any questions? Okay, there is one question.
Sir, I have a question. I have
yeah, okay, there's one question. Okay, except convolution filter, is it possible to multiply some matrix to extract the data shortly? See, the issue is that why we mean convolution. The convolution comes from from our signal processing. So the term convolution means you have to find the effect when the two signals, HT and maybe XT. Okay, it's a okay. If you look into the book of signal processing, maybe one-dimensional signal processing, okay, you can even understand what convolution does. So convolution is a sort of combined effect of a signal xt and a signal ht. And the way the convolution is done is that, as both of them are time varying signal, one is kept stationary and other is moved across that. And in each of the movement, the overlapping of the signals and the contribution of the overlap is being cumulatively added, and that results to the convolution operation. Now, when we map this to the image, what happens is that instead of the time domain information, image has a spatial domain information. So the image information varies in x and y. So instead of the function, which is xt, one-dimensional function in time, you have a function ixy, but the function is a two-dimensional function. So image is a function of x and y. That's why it's called ixy. And similarly, the convolution filter is also a function of xy. It is also two-dimensional function. So the way you move, you keep one stationary, and the other you move across it. It's the same way the convolution is done the convolution process is done in the image domain. Now this is based on a very well understood mathematical concept. Now, if you want to do something very randomly, the problem is that you cannot generalize that. Okay, you can develop some random structure of the matrix operation, and you can try to do the product of that, because fundamentally these are neural networks. So the fundamental neural network is that you have to multiply weights with the inputs. Here the inputs are your image patches, and the weights are the weights of your convolution filters, and you multiply to a dot product of this, which is same as multiplication. So that's why this entire process is called convolution neural network. It's both convolution and it's both following the principle of neural network. So that's why you do it in a very structured way, right? If you want to do it in a some matrix and in some way, right, it cannot be very well generalized, and you cannot train them very well. This structure of convolution filters, okay, helps also to train them. The training process is basically done through a gradient descent and backpropagation, by which we try to minimize the error, and we see the error at the end, and we try to find that what was the cause of the error due to the weight operations of the earlier process, and then we try to go on how the change in the weights will actually minimize the error. Okay, but as it is layered, what happens is that when you try to change something in layer n, right, you have to see that what needs to be done in layer n-1 so that layer n can be changed, and this way it will go on in backpropagation, and it will ultimately come to the first layer of weights, which will be adjusted. So this is the way how the adjustment of the weights are done. So this particular process of convolution and adjusting the weights to backpropagation works very well when you have the well-defined structures of the convolution, the patch size, the stride length, and all these things. When you have some of the random ways, if you try to do it, okay, it might not work well for the larger set of the data. Okay. Can we fix filters? Can we give filter values out of stack? This is the filters I have already told, that the filter weights. See, if you try to understand in a very simple way, don't try to think that deep network means it's really a very complex stuff. Everything is simple once you understand that. Okay. So I have already said that the convolution filters are being, the weights of the convolution filters are being placed in such a way that they can extract the features which are there in the image patches. Now, suppose take the first run of your training. Suppose try to understand the first run of your training. In the first run of your training, your filter weights are not at all well adjusted. Okay, and you are using a level data, so you know that what should be the class of the image what you have pushed in the training. And obviously, as the features are not well captured, the classification outcome what we have will vary very high from the level. Now, as the loss function is pretty high, then it will try to see that how the weights needs to be modified to make the loss function smaller and smaller. So by this process, automatically the filter weights will be tuned, and this tuning will lead to the lowest error when the feature abstraction by the filters are well mapped to the need of the classifier. And if it is done, then the classifier will have a low error, and that will settle down the weights of the filters too. Okay, next question is, what is the minimization function used for gradient descent? So the minimization function is sometimes it is actually called the squared error. Okay, it is actually we try to estimate the loss as a squared error, but normally when we try to do for classification, we actually go for the cross entropy loss. Okay, so we try to find the cross entropy, and we try to find that that how we can use the, because when we tell that we are changing the values of the weights, what it means, these weights.
Sir, you are not audible, sir.
Oh, I am not audible? Okay. Let me see. Just wait.
Hello.
I am not audible, right? Just wait.
Hello.
No, I am not. Okay. So I'm not audible?
Yeah.
Okay, but I don't know. It is.
Yes, sir, you are audible.
Okay, fine. I'm audible, right? Okay, maybe, yeah. So, okay, so the next, yeah. So this is the loss function, and normally the loss function is again dependent on the way we change the weights. So how the loss is modulated by the weights is defined by the partial derivative of the loss function in terms of the weights, right? And that's the way how it has been done. Okay. Okay, Dr. Gayatri has given a good question, that relation between the stride and the feature extraction. Yes, Dr. Gayatri, there is a relation. How close you are trying to trap the features. If you feel that the features are very spatially sparse, okay, because if you have a smallest stride, your number of convolution operations will be more. And if you have a longer stride, your number of convolution operations will be less. So you reduce your operations if the stride length is larger. But in the process, you may lose some features which are very spatially close. So this is a trade-off. The trade-off is that how you want to, what is the amount of computation you want to do vis-a-vis the guess that your spatial that your features are spatially close. So if you want to search the features spatially close, you will go for the stride 1. If you feel that the features will be a little bit distributed, okay, you can go for a stride length a little bit more. So it's a trade-off between your density of features and your computational task. So you lower the computational task by accepting that your feature density is low. If you accept that the feature density is high, your computational task will be higher. So smaller stride length will have more computations than larger stride length. Okay, so I hope that I have answered all the questions. And thanks for questions. I will again come back to my lecture. Okay. Okay. So here it goes. So I hope my screen is visible to all of you, right?
Yes, sir. You are visible.
So for a color image, so now what I have said is actually a one layer of image, which is basically for the grayscale images. But in a color image, we have 3. If I am just taking a very simple color images, which are based on primary colors like red, green, and blue. So we have 3 planes: one of red, one of green, one of blue, right? And so these are the 3 planes, right? In the right side of the arrow. And then how the filters will work? Filters will also work on the 3 planes. Right? That's the way the filters will work. So they will also work on the 3 planes, and they will also generate the filter outcomes. So we'll have different filters for different image planes, and all these will accumulate to give the outcome of a particular layer. So the outcome of a particular layer, okay, and the computation of a particular layer will be multiplied by the dimension of the image, or the number of channels of the image. This is called the number of channels of the image. In the case of an RGB color image, the number of channels is 3. Okay. So you see that the entire computation task, or the entire data, multiplies by 3 times, right? And that happens for the color images. So it's more computation extensive, but you have to sort the patterns. But you have to sort the patterns in the 3 color planes, right? So now let's try to take a difference between what is after we have studied this, okay, the convolutional neural network, and if we look into the normal neural network, which is shown in the bottom, what's the primary difference between these 2 networks? A convolutional neural network, as shown, works on image patches and tries to extract the data by operating the kernel over the image patches. Whereas in the case of a neural network, standard neural network, the entire image, that is 36 inputs, I think this is a 6x6 image, 36 inputs are entirely fed at one shot. And all the 36, so each of these nodes, each of these data elements, okay, each of these data elements here, right, will be connected to the next level of neurons by a weight factor. So if I have, suppose I have here the hidden nodes H1 to HM, okay? If I have hidden nodes H1 to HM, the number of weights I need to have is M number of hidden nodes, and each will have 36 weights, because each of the inputs are connected to each of these nodes. So H1 will have 36 weights, H2 will have 36 weights, HM will have 36 weights. So M number of hidden nodes will have M cross 36 weights. So it's a huge number of weights. This is how many weights we require here. You see how many weights we require here, right? Here, for each kernel, we require 3 weights. See, for 9 weights, sorry. It's a 3 cross 3 kernel. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 weights. And if we have M kernels, which may be same as the number of hidden nodes, we have M cross 9 weights. So if you have, assuming that there are same number of kernels as the same number of hidden nodes in a particular layer, your convolution filter will have M cross 9 weights. And that's a pretty huge reduction in the number of weights you need to adjust. And that's the gain of the convolution filter. So I quickly go to this. So this is the case what we have, as we told. As I already told you that. So this is the same scenario has been repeated here, right? So the next step is obviously there is another way to reduce. So why convolution kernel helps? Convolution kernel not only does the reduction in the feature space, okay, by reduction in the number of weights, but it also reduces the spatial depth without losing any information. How it does it? So what it does, okay, after you generate this convolution outcome, what I show here is that I show filter 1, its convolution outcome, and filter 2 on the right with its convolution outcome in the right below. So these are the 2 filter outcomes I have generated after working on my image. Now what max pooling does? Max pooling takes a window, and in the window, it takes the maximum value. So if I do the max pooling, so I can, if it is a 2 cross 2 window, if I assume that my pooling window is 2 cross 2, then in each 2 cross 2 window, it will only take the maximum value. And what happens is if you see the extreme left window, the maximum value is 3, next 0. Okay, so this way max pooling works. This, what it does, it actually represents a larger spatial dimension without losing the important information in a much smaller spatial dimension. Because once we represent these 4 pixels with 1 pixel, you have reduced the dimension of your information by 1/4. Because 4 pixels are now represented by their max pooled information. Or 4 feature values are represented by their max pooled feature values. So you reduce the speed, okay, and that's called the subsampling. And the subsampling works fine. It reduces the spatial dimension, but it still traps all the important features. Okay, the features which are important, the features which are prominent, because you're selecting the maximum value in the pooling window. So you're selecting the maximum, so selecting important features which has contributed in an important way. So this is what is the CNN. So reduces the connection, and okay, it's a shared weights on the edges. Okay, and max pool further reduces the complexity. Okay, so this is the way it actually works. Though here I haven't introduced the ReLU layer. You can always introduce the ReLU layer after max pooling. So what it does, that if there is any negative values are still there, okay, you can discard them if you are using ReLU. Or if you're using something like a sigmoid function or tanh function, you are taking the taking the higher values, okay, and you're discarding the lower values. Okay, so this is the way you try to regenerate the image in each cycle of your convolution, right? And this is the way you go on abstracting the higher order features from an image. And at last, what you do, you actually apply the same neural network. After you have done enough feature building, okay, you have abstracted the high level features, then those high level features can just feed a neural network, okay, as a normal neural network. And it's called a flattened network, because it is not now layered. All the previous analysis was done on layered. Okay, each of the layer consists of multiple kernels, multiple outcomes. Now all the outcomes, okay, are made a single one dimension, and that one dimensional feature information feeds a neural network, a feed-forward neural network, which is a normal neural network classifier. And this neural network classifier identifies the object very clearly. So if I try to make it very simple, each of the colors in the left is the outcome of the different filters in the previous layer before the flattened. But once we flatten, this layer goes off. You just pull everything as a one string, right? And that becomes a flattened network, right? And then it feeds a classifier, a feed-forward network, which is a standard neural network. And these are your classes, okay? These are your class outcomes. 1, 2, 3, and 4. These are your class outcomes. And you can train that. Okay, you have trained the network. Okay. Now, okay, I end about the fundamentals of convolutional neural network, how it works on the image. And now I go to the advanced portion, advanced discussion, okay, of how I can use the convolution features to analyze my video. Okay. To understand this, we have to know a bit about the video and how the idea of image can be extended to analyzing the video. So image, what I have defined as a function of xy, ixy. In the case of video, the third dimension comes. And the third dimension is the time dimension. So an image frame which is varying in time, which means that ixy is a distribution which varies with xy. Ixyt is a distribution where the ixy varies in time. What it means? It means that in frame 1, your car or an object was at the top uh, left corner, and after some images you find the object in the middle of the frame, and maybe after some frames you have found the object at the bottom corner. So which means that the object has moved from the top left to the middle to the right bottom. So which means that the IXY has been changed over the time. If the IXY doesn't change, doesn't change with time, it's an image. The image I capture will remain the same after a long interval of time. But if it is a video, I will see that the information, information changes with time. So what I can abstract is that a number of IXYs coming in a given interval of time, right? And there are some parameters like frame rates, which tells you that how the video is defined. So how the number of frames captured within an interval of time is being considered for a particular video. Okay, so that's the concept of video. So you have to understand that in the case of video, you have to take the third dimension, which is the time. Now, what are the applications? As we have image has a lot of applications, video will have a lot of applications also, right? And these applications are in your computer vision for robotics. They understand the movements of the objects, and they try to act just like a common human being. Like we can understand the objects, and we can interact with objects as they're moving. Similarly, robot can do the same. The domains like unmanned vehicle, where the vehicle tries to move on the road on its own, tries to look at which objects are moving, which objects are static, and tries to follow the signal, and tries to go as per the traffic. So it has to also understand the movement of the other cars in the same road. So it's also an analysis of the video, because they completely work on the data captured by the sensors. They analyze the data automatically, and based on the analysis, the control system of the car works without any human intervention. And that's why these are so interesting domain. The other aspect of video analysis is the human activity, be it sports, be it surveillance, be it training, be it actually monitoring or actually doing a sort of helping the elderly people in their work, and obviously the domain of medical image analysis in terms of video. There are a lot of information, video information in the medical image, in the medical analysis and medical surgery takes place nowadays. If you have a non-rigid object, the object in our body which moves with time, like your heart, like your many of the objects in the body, like your blood flow, like your, I think, in the lower abdomen of your body, right? They also moves with with time. There are movements with the time. So to understand those, and to do guided surgery, you need to analyze the video very well in the medical image analysis. Apart from this, there are many more. These are some very important video analysis problems or video analysis applications I have tried to tell you. Now, why is motion useful? Because motion is the information, is the dynamic information in a scene. Okay, and this dynamic information needs to be understood so that you can take proper decisions. So the very fundamental way to understand the change in subsequent image frames of a video is based on a theory called optical flow. Okay, what is optical flow? Optical means the information which can be visualized. Okay, the information which can be perceived by your optical senses. And the flow means there is a movement. Means that information which existed in a particular area or particular position has changed with time. And if you can track the change, which is called optical flow, then we can actually find out the temporal parameters, or we can abstract the change in the image information in a given video very accurately. But you have to understand the change in the image information, the predominant part is the movement of objects. But sometimes there are some other means which we need to discard. Suppose the object remains the same in the same position, but in frame 1, the intensity was something, and in frame 5, the intensity was lower or higher. As the intensity changes, okay, as we know that the image information is a product of intensity and reflectance. Intensity means how much amount of light energy is incident on the object, and reflectance is out of that energy, how much energy is reflected by the object, which is captured by your sensor. So if the intensity is reduced, means from the bright noon, you have come to the evening hours, when the intensity itself changed, that will also give a difference in the image information in the same region of the image. But this is not due to the movement of the object, but due to the change in the intensity or the brightness. So that is also we have to take. We will not consider those cases as the object movement, though that will create a difference. So those are some of the sometimes those are the difficult things which we need to consider. Okay. Okay. So those are different things we need to consider in the case of video, and we need to see that how those things can be properly taken care of. But in this discussion, I'm not discussing those issues apart from the movement of the objects in the video. So our goal is to recover the image motion, the motion information of the pixels using optical flow. So the optical flow features are identified by vectors. Okay, they are identified by vectors. What are these vectors? How the vectors are created? These vectors are created between the subsequent frames. So a particular image information which existed in XY pixels. Suppose let us try to localize the change in information to a pixel level. Okay, though it's normally done in the object level, an object consists of several pixels. But let's try to understand it in a very simple way. So a pixel information which was XY in image Tth time interval. Now the same information has moved to the pixel position X dash Y dash in T plus 1. And if the difference between XY and X dash Y dash is considerable, which means that which is a higher than a threshold, then I will consider that this is due to the movement of the pixel. And then I draw a vector. Okay, and then I draw a vector. Okay, from XY in frame T to X dash Y dash at frame T plus 1 or T plus N. And that vector is called the optical vector image, okay, the optical flow vector or the motion vector, which defines optical flow. More and more vectors we generate, it means that the video has more motion, and longer length of the vectors we generate, that defines that the change has done rapidly. Because the length of the vector means that how the difference between X, Y, and X dash Y is large or small. If it is large, it means that the change has done within a very small amount of time. If it is small, it means that the change is slow. So sometimes using optical vector, using vector, we can address the speed of the vehicles. Now I come back to some history by which I got associated with this term optical flow and this in a very early in my research career. Okay, I hope that Dharmendra can also remember something out of that. So I was teaching in an institute, Meghnad Institute of Technology, 2002 to 2005. But Dharmendra was also my student there, and there I was. That means I got a project grant from DRDO, and it was very special for me because it was very difficult for any faculty from an institute, young faculty from an institute at that point of time, to get a grant from DRDO. So we got a grant from DRDO in the College of Meghnad Institute of Technology under my principal investigator supervision. And the problem what I dealt with in that particular is the same problem. So this was a problem which was given by a lab of DRDO called VRDE, Vehicle Research Development Establishment, which is a place little bit far from Pune, 3 hours drive from Pune, and it's called Ahmednagar. And the problem what we had is that we have to develop an algorithm, which will sit on the. At that point of time, DRDO started thinking about unmanned ground vehicle. So our problem was to develop a software, a tool, which will work with the camera vision system of the vehicles, of the defense vehicles, and will give an information that which obstacles are moving and which obstacles are stationary. Okay, so this was a partial task of a greater task, but the project UGV they had. So that's my connection with video analysis and image analysis and optical flow. So I remember just to make the things a bit out of the tough theoretical context. I tried to make you motivated that this is a problem which is existing for the 15 plus years. still if you see the latest papers in CVPR, Computer Vision Pattern Recognition, which is a topmost conference of IEEE in this domain, still the optical flow is being very highly considered. Okay, so let's move on. So this is what I said is optical flow. So if you look into these two figures, one is IXYT minus 1. Okay, these positions of the pixels are IXYT minus 1, which is the previous frame, and this is the IXYT, which is the next frame. And if I just superpose IXYT on IXYT minus 1, and we try to find the vector difference of the corresponding pixels, we will find what is called an optical vector, what is called a motion vector or an optical flow. Okay. We have to tell that the assumptions what we have taken is that the brightness is constant, because as we told that if the brightness varies between two frames, the information changes without the movement of the objects. And obviously the second thing is that its motion is small, not very fast. Because if it is very fast, I will not get anything in the subsequent frames. I can see a change, a very huge change in a frame which is a long distance. Another one is the spatial coherence of the surface of the objects. Or the surface of the objects are actually they move together, which means that these are all rigid objects. In a rigid object, all the surface points move together. If it's a non-rigid object, then the surface points can move in a different way, which we are not. So these are the key ideas which are started from. It's a not that these ideas are very what I can say very okay. These are very recent ideas. Okay, we have to know this research of spatiotemporal fusion, which means that we are trying to do the convolution or deep network operations on the spatial information which I've already seen. But not only the spatial information, we are also using the temporal information using optical flow. These are started from 2013, 2014. So it's only 6-7 years. 6-7 years. Okay, in a strong domain like video is nothing. Okay, there are problems existing for 20+ years. Okay, so these problems are still very fresh, and a lot of submissions we see in the good conference and journals in this particular domain. So the students and faculty members can surely get involved in this particular very interesting domain of research and analyzing the video. So this particular problem domain is called spatiotemporal fusion. Okay, and the models which are there. So one way we can analyze the video, because when we do spatiotemporal means it's a video data, because each image has a spatial distribution, and if I take multiple images for a video, it's a temporal distribution. So spatiotemporal distribution itself means it's a video itself means a spatiotemporal distribution. So abstracting the features, so working a convolutional neural network on these spatiotemporal features. The first work in the literature we find is a work in 2013. Okay. In ITB transactions. So the technique is called 3D CNN, three-dimensional convolutional neural network. What's this? Instead of doing the image convolution on the image, they have stacked the image information in time. Okay, so they have made multiple image frames. Okay, it may be 5, it may be 7, it may be 10. I think the paper tells about 7. So the 7 image frames. Okay, so the video is being cut into sets of 7 frames, and each of the 7 frames gets into the CNN. Now what happens? As you have seen the RGB 3 planes, all the kernels works individually on the 3 planes, what will happen now? All the kernels will individually work on the 7 planes. And so the number of feature planes will increase. So the number of image frames multiplied by number of kernels will be the number of convolution operations. And each convolution operations will have 9 weights. So multiplied by 9 will be the number of weight. So you can understand that though we can go on doing and the rest operates in the same way, right? You do a pooling, okay, you again apply another set of filters, okay, you can use a ReLU and you can go on doing this, and then you can make the network fully flattened. But the way it works is that it is a very high dimensional network, as I told you, right? So many features. Okay, number of convolution curve filters multiply the number of frames in that particular 3D CNN, multiply by the number of weights. So it's a large number of information you have to handle. Okay, if you look at the difference between the 2D CNN and 3D CNN, there is a difference, pictorial difference on the left. Okay, what is done if you see that pictorial difference is that for each kernel here each kernel works on a particular image. So the patch is generated on one image, whereas in a 2D kernel, in a 3D CNN, the patch is done over all the temporal frames. Over all the temporal frames, the kernel works on the patches. So it's a more number of computations. And similarly, if you see the mathematical part of it, the operation weight multiplied by the patch, okay, which is the W and V. V is the patch, okay, and W is the weight. Okay, it works on P and Q are the dimensions of the patch as well as the kernel, and the M is the number of kernels. Here, in the case of 3-dimension, you have an extra parameter R. What is the R? R is the number of image frames, what we pass in a 3D CNN. So the number of image frames in the 3D CNN. So it is the patch dimension multiplied over number of patches, number of image frames, and over that number of convolution kernels. So you have R, you have Q, you have P, and you have M. So there are four parameters of actually controlling this convolution, right? The other figure, which is here, right? This particular figure shows that the dimensions, what we have, okay, here, right, will go on into all the subsequent layers, right? And it will be a multi-dimensional feature space, okay, in terms of the depth. So what we have here is that we have an extra axis, which is the depth axis, okay? Here is the depth axis. So we have the spatial axis, the length and width, which is already there, but the extra axis is the number of frames we plug, and that's the depth axis. So based on the depth axis, we will also have a depth in the convolution outcomes. And that's all, right? So this 3D CNN started in 2013, and people still use it. It's not that it is not, it's not used. It's still used it. Yeah, people still uses it, but it's a pretty costly. So it requires a good amount of resources, right, and computational time to train that. The next step Okay, the next progress in this particular domain is called a two-scale fusion or two-scale convolution model, which was proposed by 2004 in a CVPR paper of 2014 by the group of Karpathy. Okay, they proposed a different way to do this. They told that when you're working with a video and you're doing a 3D CNN, don't try to work with the entire image data. Okay, don't try to work with the entire image data. You try to reduce the image data what you put and try to make two channels. Channel 1 is called the phobia and channel 2 is called the context. Now, what is phobia? Phobia, that if we look into an image or a real scene by our eyes has a region called phobia region, and that phobia region is responsible for capturing the maximum information of the scene, and that's mostly the central part of the scene. So we observe anything which is centrally located very clearly than the things which are the side located. So if I give you a picture, okay, you will very quickly find if something is there at the center of the picture, right? And if there is something at the corners of the picture, it will be a little bit like a time you will require to understand those. Why? Because our phobia is located at the center, and the phobia captures center information. So what it does is that it actually generates two streams from the video. One is the phobia stream and one is the context stream. Both are heavily reduced in size compared to the actual video stream. Why? Because phobia stream only captures the central part of the video, and context stream is an average, is a sort of subsampled information of the video, which means that it covers the gross information of the video, but not the detailed information of the video. So the gross information, okay, using the gross information, you try to generate some features, and using the central information, you try to generate the features, and you then merge the two features, generate the feature plane, and you try to then classification. So abstracting the features will be same as we do in the convolutional neural network. So both the frames goes to the 3D CNN, but here the thing is that means the video or the image dimension are much reduced than the actually what we do in the 3D CNN, and this is called a two-scale convolution model. Now, there are some standard way to define that what are these particular fusion approaches. Okay, so the first one is called a single frame. Single frame means you take a video, fragment the video into shots. I think some of you know what is shot. Shot means when the background of the video doesn't changes, only the foreground changes. Okay, or you can also define a shot defined by some interval of the video. So in each shot, you take one frame, right? And you try to analyze that. It's called a single frame. Okay. You can do a late fusion where we take two frames, one at the start of the shot, one at the end of the shot. One is called early fusion, where we take a few image frames in a very central portion of the sequence of frames. And another one is called late fusion, which is a multi-stage fusion, which means that we first try to fuse the information from the neighboring frames, and then we try to fuse the information of those neighbors in the next layer, and next layer, and next layer, and so on. So this is a slow fusion which actually tries to develop the information, or tries to extract the features for the entire video, but by cutting it into small blocks and then actually doing the aggregation of the features of the blocks in multiple levels. So these are the different classical fusion approaches. Now, sometimes it is being seen that the slow fusion works good. And if you try to be very extensive of this, you can do a sort of approach where you try to do all the fusions and try to find which one is giving the best. Okay. The last one, what we try to tell is that using the optical flow. So it's called a two-stream convolution. Okay. In the two-stream, what is done in the video means again a number of frames. In the video, you take an image which is located somehow in the central region of the particular number of frames. And that's only one image frame you take, which gives you the overall spatial information of the video. And across the number of frames, you take the optical flow information. Okay, by the vectors information like this, the D vector, the displacement vectors. Okay, so the displacement vectors have been computed between all the frames of the video. But obviously, the video will be some short duration, because if you are making this gross over the entire video, it will not be good. You try to cut the video into segments, and for each segment you do this. So there's a spatial stream and there's a temporal stream. Spatial stream takes one image from the entire video, okay, which can be the central information or the reference information. I think those who know video compression, they know what's the reference information in a particular video. Okay, it's called the I frame, right? And the rest frames are the optical flow information. And you try to extract the features from the optical flow domain also, and as well as spatial domain also. And then you try to fuse them, and then try to generate or try to classify the image based on the video, based on both the spatial as well as temporal information. Okay, and that is also a very good technique which has come up in 2014, which is called two-stream convolution. Okay, this is also a technique which is a sort of fusion, which is a little bit different. Okay, it is not that the two streams are working independently like the previous case. It's a work in 2016 where you try to mix the time frame and the spatial frame in some layers, in some levels, and then again perform convolution on the fusion on the fused information. Okay, so this is what is done. So if you see this is this particular technique. Sorry. This particular technique is called the two-stream network fusion, where
recording in progress.
Where you see that this is the temporal frame, this is the spatial frame, right? And the temporal frame progresses a bit in the feature space, spatial frame progresses a bit in the spatial space, and then we merge, and then we again take a combined feature space. Unlike here the two streams actually progresses distinctly, and then when we generate class code, then we fuse the two streams. But here it is more fusion in real sense. We actually fuse the features of the temporal and the spatial frame, and then we continue to extract the features on the fused feature space, right? And that helps you, and that gives a better classification outcome. You can do a feature space very equally, or you can also do the feature space and hybrid. So if you see this diagram, right? You see that this fusion is being done spatial and temporal mixed. This is continuing the spatial, and then again there is a mix between the entire spatial and the hybrid of temporal spatial. So there are different types of combinations of fusion are being done, and this is being presented in CBPR 2016 on the two-stream network fusion. This is a little bit different. This is actually called a linear encoding of TLE network. This is very recent, done in 2017. So this is the spatial stream. This is a temporal stream. So what they do, they actually try to generate the features of the different stream differently, independently. And these features, they try to encode it in a particular way. Okay, they try to form a vector, okay, out of the features formed in the temporal and the features formed in the spatial. And then they try to combine these two vectors, okay, which is through some encoding process, right? The spatial stream vector and the temporal stream vector, right? Through some encoding process, they generate a vector by concatenation of the two stream vectors. And now this vector is used to classify the video. So this vector is a signature of the video, right? And this vector will differ from video to video. And the process is much easier than a fusion and generating the feature space, but it takes a lot of effort in encoding it properly. So this is another technique which is defined as a linear encoding networks and published in CBPR 2017. So in a nutshell, what I have discussed till now is a predominant way to analyze video, which maybe the action classification is one of the one of the important application, is that use a 3D convolution network, use a stack of images from the video, and use a 3D convolution network. Next is you can use a spatial frame and an optical flow frame, and do the convolution network of the both, and then you fuse them, which was actually two streams network, what I showed in 2014 CBPR, two stream network. One is a spatial stream and one is the optical stream, a temporal stream. The other one is 3D convolution network on both. That means spatial stream 3D convolution network, temporal stream 3D convolution network, okay, which is fusion of the two 3D convolution network streams. And there's also something which I will not elaborate here due to limitation of the time, is that you can also use a sort of LSTM type of networks, okay, which tries to capture the sequence information in the network, right? And what you can feed the outcome of the convolution networks, okay, in the temporal domain, okay, outcome convolution network, and then you can feed it to the LSTM, the feature, how the feature sequence changes, and from the LSTM analysis you can generate the actions also. So this can also be well done. So these are different variants of the way the fusion can be done in the video domain. So this is what is called modeling of sequences, okay, using the RNN or LSTM type of techniques. Okay, sometimes we tell it's a one input, but to generate number of outputs by analyzing the sequence of images. So you give image one by one, or you give your input one by one, right? And it generates the annotation of the image. It's called image captioning. There's also one analysis called many-to-one, which is basically you give different words, number of words, and you just generate one single sentiment whether the person is happy or good. And another one is many-to-many, where you give a number of words in one language and you generate number of words in another language. Like you give a language in English and you generate a language in Hindi. So there are different types of sequence analysis are there, and the LSTM model is a long short-term memory model, which works very well in understanding the long sequences, and they can also be very well used in the analysis of the fused information. So I will come to the last part of my lecture, the futuristic applications of this. At present, we are trying to. At present, we are trying to analyze the videos. That's okay. But within the videos, there are relationship among the objects, which is called spatial temporal localization. So in a particular image, the two objects are close, or two objects are doing some activity, and once the frame changes, the activity of the two objects changes. And this is the next level, which is also some way it is also called co-segmentation. Where there are something very closely related topic is co-segmentation, where we try to find the relationship between the segments in the successive video frames. Okay, so these are some of the recent works which are coming up in analyzing the video, and it's a very interesting work where the students and the teachers and faculty members can get engaged. So I come to the end of my talk. As I told that I will speak this for around one hour, 120 minutes or 110 minutes. So I nearly almost 2 hours I spoke. So to summarize what I discussed with you or what I lectured is that we have seen the detection and classification of the information or the activities in the video has a wide range of application. Spatiotemporal information is the key in understanding the video information. We can use the recent techniques using deep networks to analyze the spatiotemporal information by the spatiotemporal fusion strategies. Different strategies have different cost and performance trade-off. So some strategies are very good in performance, but they're very costly. So for a given application, you need to understand the trade-off, and accordingly, you need to choose the particular particular approach of solving the problem. And that's all from my end. I hope that I have given a brief insight of the deep network analysis of image and how we can progress towards the video analysis using the spatiotemporal fusion. And I end here. And now I will be happy to take some questions.
Thank you, sir, for this wonderful lecture. I have sent you some question in your chat section.
Yes. I will try to answer one by one. Let me take the question where I left. So, okay. So what is the role of backpropagation in the artificial neural network? So as I told that, backpropagation is, you get the error after you have evaluated your network. So it comes at the last of your network. But the amount of error will tell that whether you need to adjust your network or not. So from the error, estimation of the error, you need to move backwards and go on adjusting the weights in the kernels. Because if you are adjusting the weights in the kernels of the second layer of the pre-final layer, those outcomes are dependent on the pre-final layer. So you have to go to the pre-final layer. Okay, and in this way you will see that ultimately the weight adjustments you have to do at the layer 1 also. So actually backpropagation is the movement in the backward direction in a network. So how can I choose the best kernel for a good model? If you use 2 correspondence layer of flattening, it's possible to have a good result. Okay, this is a good question. So So flattening layer is somewhere where you have built a feature space, right? Sometimes you can use the initial flattened input layer, just like you do the hidden network or hidden layer in a real neural network. You can use multiple hidden layers also, and then you can actually feed the classifier. But you have to again plan that. That means how much performance and how much quality you require. Whether you really require that, because sometimes the feature space is so well generated by the highest convolution layers that a decision is pretty easy. Which means that you have a beak, you have a tail, you have a wing, you have a leg, right? And so it's a bar. So you have features like beak and this, so you can easily tell that it's a bar. But if the feature space is not yet well built after the final CNN layer, you might need to use a neural network which is having multiple hidden layers or multiple flattened layers. Yeah, you might need, but you have to see that whether your convolution outcome is not enough to do that. Okay. Can we use this technique in sentiment analysis of a phase in video or predict the future sentiment? Yeah, obviously video analysis, you can obviously do the sentiment analysis in the video, because there is a correlation in the movement of your faces, and those correlations can be very easily identified by the sequences of the faces. Right, by the sequence of the faces, you can well understand that how the sentiment is going. Right now, prediction of future sentiment you can always do. Right, you can always do by using something called a GAN type of network or generative type of network. Okay, generative networks are basically predicting the next. You can do that. Okay, but okay, these are okay. You have to. So when you're using a generative network, you have to train it in an appropriate way so that the next sequences can be generated by the network. In a normal CNN network, is basically for classification. Okay, you have to use a generative network based on your CNN feature space to actually predict the next features next faces having sentiments. Can we use multiple network in Fusion? Yeah, that's true. So we are using multiple networks. So if you're telling that multiple spatial flow, yeah, we are doing multiple spatial flow in the phobia and context network. In the phobia, we are taking the central information, and the context we are taking the subsample information. So this is a multiple network fusion, right? So we're doing that, and obviously we are also doing the fusion in optical flow and spatial flow. To use loops in between the network of fusion to detect movements. Okay, so we want to tell that actually these are done by the fusion what I have shown, where you fuse the spatial and temporal in between, and then you go on generating the feature space after that. So in those networks, you actually correlate the spatial features and temporal features, and then take a hyper feature space which works on the correlated feature space. And there, this type of connectivity between the temporal and the spatial features are established early. Okay. Yeah, there are different. Yeah, there are techniques called handcrafted features where we try to extract the features in the in the formal procedures of machine learning and try to fit them with the network. But I have to see that whether in the fusion, in the spatiotemporal fusion domain, such works have been done. Right? I didn't explore that much to find that whether the handcrafted, this is called a handcrafted features, whether the handcrafted features are also used. Here, I didn't. Okay, I have to explore whether the work exists, but in the standard CNN, the fusion of the CNN with the handcrafted features is a very standard technique. Okay, this is called speech characters and lip movements. Okay, so this is a very important thing. Okay, so I didn't show that there is a good experiment done by MIT professor, right? Where they have actually put the word of the president of US to the lip of a particular person. I think the professor himself. So professor himself was uttering the voice of the president of America, how it works. So it's called a cycle procedure. So it's a cross domain. One is the audio domain and one is the video domain. So you have to train the audio domain with respect to video domain and also video with respect to the audio. And then there are techniques called cycle GAN, by which you can find latent feature space. I also give a very popular lecture of latent feature space. I think there is one of the lectures which has been recently available in the ICOA. This is a conference in Germany which happened in this May, and my lecture is there on 20th May. So in 20th May, if you see the ICOA lecture, right, you will find my lecture on autoencoders and GANs, and where these techniques are being used, where the audio spectrogram, it's called a spectrogram, is mapped with the video, and you can do this type of things, but things are not so easy. But there are research work which have shown that this can be done. Okay, so Jilam, I hope that I have finished all the questions which are there in the chat box.
Yes, sir. And thank you for giving us this wonderful lecture. And we hope in future we will expect more this type of good lecture from you. And we have a small token of appreciation for you.
Yeah, so thanks, Jilam. Thanks to the college. Thanks, Dhanpal, for this wonderful appreciation memento for me. And thanks. I will be happy to contribute in the same way in any of the future occasions. Thank you all. And please, if you have any further doubts, please pass the email of Jilam. You know my email. You can pass my email so that the students and the faculty members who are interested to contribute and work in the domain, they can surely connect.
Okay, sir.
Thank you all. And I am leaving now, right?
Yes, sir.
Okay. Thank you all. Thanks.
Thank you, sir, for your wonderful session, sir.
Okay.
So, Sheila, madam, we can now close this one.